Let's consider this problem. A 300 kilogram block hangs on a 2-meter long aluminum cylindrical rod with a diameter of 0.5 centimeters. We're given the elastic modulus of aluminum. What is the change in length of the rod? So let's say this is the rod before we added the 300 kilogram block to it. Now once we add the block, the rod is going to increase in length. We need to calculate the change in length. So basically, we need to calculate delta L, which is the difference between the original length, which is L0, and the new length, L final. So feel free to pause the video if you want to try this problem. Now the formula that you need is this one. Delta L is equal to 1 over E, where E is the elastic modulus or Young's modulus of aluminum, times the force divided by the area multiplied by L initial. Now let's not forget that we still have a 300 kilogram mass hanging on the rod. Now we're given the diameter of the cylindrical rod. So I'm just going to draw a bigger version of that circle. So the diameter is 0.5 centimeters, which means the radius of the circle has to be half of that, which is 0.25 centimeters. Now we need to convert the radius from centimeters to meters. So we got to divide it by 100. So 0.25 divided by 100 is 0.0025 meters. So that's the radius. And because this is the shape of a circle, the area is pi r squared. So now let's plug in everything that we have. Also, what is the force exerted on the rod? That's the only thing that we're missing. And we have the original length of the rod, it's 2 meters. Now the force is basically the weight force of this object. It's equal to mg. So delta L is going to be 1 over E, that is the elastic modulus, which is 70 times 10 to the 9, multiplied by the force, which is mg, that's 300 kilograms, times 9.8, and that's a terrible looking 8, divided by the area, which is pi r squared, so that's pi times the square of the radius, 0.0025 squared, multiplied by the initial length of the rod, which is 2 meters. So let's multiply 300 by 9.8 and by 2, and then divide that result by 70 times 10 to the 9, and then divide it by pi. You can do it one step at a time if you want, and then divide that by 0.0025 squared. So the value that I have is 4.278 times 10 to the minus 3 meters. Now if you want that answer in centimeters, just multiply by 100. So the change in length is about 0.4278 centimeters. So what about part B? What is the new length of the rod? The change in length is the new length, or the final length, minus the initial length. So the new length is going to be the change in length plus the original length. So that's going to be 0.004278 plus the original 2 meters. So the new length is just about 2.004278. So it really didn't change much. It's about the same. It stretched a little. Now what about part C? Calculate the tensile strain of the rod. The tensile strain is equal to delta L divided by the original length. So that's 4.278 times 10 to the minus 3 meters divided by 2 meters. So that's 2.139 times 10 to the minus 3. So that's the fractional change in length. Notice that the tensile strain is unitless. So if you want to turn this into a percentage, multiply by 100%. So that's 0.002139 times 100. And so the length really changed by maybe about 0.21%. So it didn't change much. Now let's move on to part D. How much tensile stress is applied to the rod? The tensile stress is going to be equal to the force divided by the area. And the force applied is the weight of the block, mg. And the area, just like before, is pi r squared. So the mass of the block is 300 times the gravitational acceleration of 9.8, and the radius, which is 0.25 centimeters, that's 0.0025 meters. So you should get a very large number, which is 149,732,970.5. So we could say that's like 1.5 times 10 to the 8th power. And it's newtons per square meter. So if we want to round it. So that's the tensile stress that's applied to this object. Now here's a question for you. The ultimate tensile strength of aluminum is 200 times 10 to the 6 newtons per square meter. So the ultimate tensile strength tells you the maximum stress that you can apply before the aluminum rod will break into like 2 parts or multiple pieces. So under this situation, will this particular aluminum rod, will it snap? Will it fracture? Well, let's convert this number to 10 to the 6. So 8 is basically 2 plus 6. So 10 to the 8 can be written as 10 squared times 10 to the 6. And 10 squared is 100. 1.5 times 100 is 150. So this is equivalent to 150 times 10 to the 6 newtons per square meter. So notice that this number is less than the ultimate tensile strength of aluminum. So if we place a 300 kilogram block, the aluminum rod will not break. Number 2, a 5,000 kilogram block rests on a column of concrete with a diameter of 10 centimeters. What is the compressive stress applied to the column? So let's draw a picture. So let's say this is the column. And let's say this is the ground. And we have a 5,000 kilogram block resting on the column. And we're given the diameter of the column is 10 centimeters, which means that the radius is 5 centimeters. What is the compressive stress applied to the column? So the block exerts a downward weight force, which causes the column to compress or shrink in length. Now to calculate the compressive stress, we know that stress is the ratio between force over area, and the force is the weight of the block. So that's mg, and we're dealing with a circular column, so the area is pi r squared. So it's going to be 5,000 times 9.8 divided by pi, and the radius is 5 centimeters, which is 0.05 meters. So the compressive stress is 6.24 times 10 to the 6 newtons per square meter. Now let's move on to part B. Calculate the compressive strain of the column. Now this is going to be different because we don't know the length of the column. We don't have L0. So how can we calculate the strain without knowing the length of the column? Because the strain is equal to delta L divided by L0. So what should we do? The second way in which you can calculate the compressive strain is by using this equation. The elastic modulus is the ratio between the strain and the stress. Well, stress over strain, not strain over stress. So we have the stress and the elastic modulus. We just got to calculate the strain. So let's cross multiply. So the elastic modulus times the strain is equal to the stress. So if we divide both sides by the stress, what I meant to say was if we divide both sides by E, the elastic modulus, then that will give us the strain. So we can calculate the compressive strain by taking the compressive stress and dividing it by the elastic modulus. So the stress is 6.24 times 10 to the 6 newtons per square meter, and the elastic modulus is 20 times 10 to the 9 newtons per square meter. So these units will cancel, and we know that compressive strain is unitless. So we're going to get a small value, which is 3.12 times 10 to the minus 4. So that is the compressive strain of this particular column. Now what about part C? If the ultimate compressive stress of the concrete column is 20 times 10 to the 6, what is the maximum force that can be applied to the column without it breaking? Now looking at our answer in part A, the stress that we have is 6 times 10 to the 26. It's less than the ultimate compressive stress. So that means that this column can support a mass of 5,000 kilograms. In part D, we're going to see the maximum amount that it can support. But let's focus on part C for now. We'll get to part D later. Now you need to know that the ultimate compressive strength, which I'm going to call C, is the maximum force divided by the area. So if you wish to calculate the maximum force, it's going to be the compressive strength times the area. Now let's calculate the area separately. We know it's pi r squared. So that's pi times 0.05. Keep in mind the diameter is 10 centimeters, so the radius is 5 centimeters, which is 0.05 meters. So the area is 7.854 times 10 to the 3 square meters. So now let's calculate the maximum force. So it's equal to the compressive strength of 20 times 10 to the 6 newtons per square meter multiplied by the area of 7.854 times 10 to the minus 3 square meters. So as you can see, the unit square meters will cancel, leaving us with units of force, which is the Newton. So the maximum compressive strength is 157,080 newtons. Now, what is the maximum mass that the column can support? So the force is based on the weight force of the block. So the maximum force is equal to mg. So the mass is going to be the maximum force divided by g. So that's 157,080 newtons divided by 9.8 meters per second squared. So the maximum mass that the column can support is 16,029 newtons if you round it to the nearest whole number. I mean, not newtons, but kilograms. So that's the maximum mass that the column can support. Number 3. A cube with a side length of 10 centimeters is made up of aluminum metal, and we're given the shear modulus. A horizontal shear force of 50,000 newtons is applied to this cube. How far will the top of the cube move in the horizontal direction relative to the bottom of the cube? So let's draw a picture. So all three sides of the cube are the same. The length, width, and the height of the cube are all equal. Now I'm just going to draw just one side of the cube. So we're going to apply a horizontal force, and the ground is also going to exert a force. At the same time, as we press down on the cube, there's going to be a force in the negative y direction, and the ground will exert an upward force in the positive y direction. But we're not going to be concerned with those forces in this example. Now, as we apply a force, the shape of the cube will look like this. It's going to deform a little. So this is L0. And this is delta L, which is what we're looking for. We want to see how far the top of the cube move with respect to the bottom part of the cube. So the bottom is still here, but the top is now in this position. So our goal is to calculate delta L in part A. So the equation that we need is this one. Delta L is 1 over g, the shear modulus, multiplied by the shear stress, which is force over area, times L0. So g in this example is 25 times 10 to the 9, and the force is 50,000 newtons. Now the area, which is length times width, so we have a length of 10 centimeters and a width of 10 centimeters. So that's 100 square centimeters, but we need it to be in meters. 10 centimeters is 0.1 meters. You got to divide it by 100 to convert it to meters. So the length and the width is both 0.1 meters. So the area, which is 0.1 times 0.1, that's 0.01 square meters. And L0 is also 10 centimeters, which is 0.1 meters. So it's going to be 50,000 times 0.1 divided by 25 times 10 to the 9 divided by 0.01. So the change in length is very, very, very small. It's 2 times 10 to the minus 5 meters. Now let's convert that to millimeters. Let's multiply by 1,000. So this is only 0.02 millimeters. So if you apply a horizontal force of 50,000 newtons to an aluminum block or an aluminum cube that's 10 centimeters on all sides, the effect on the block is not noticeable. It's very hard to see a change in length of 0.02 millimeters. It's very difficult to see 1 millimeter, and this is 50 times smaller than that. Now let's move on to part B. So what is the shear stress applied to the cube? The stress is simply the force divided by the area. The force is 50,000 newtons. and the area is 0.01 square meters, which we got before. So this is going to be 50 million, I mean not 50 million, but 5 million, which is 5 times 10 to the 6 newtons per square meter. So that's the shear stress that's applied to the cube. Now let's calculate the shear strain. The strain is going to be the change in length divided by L initial. L initial is 10 centimeters, which is 0.1 meters, and the change in length was 0.02 millimeters, which is 2 times 10 to the minus 5 meters. So the strain is 2 times 10 to the minus 4. Now keep in mind, you can also calculate the strain using another formula. The shear modulus is equal to the stress divided by the strain. So if you need to calculate the strain, you can take this shear stress and divide it by the shear modulus. And the shear stress was 5 times 10 to the 6 newtons per square meter. And the shear modulus is 25 times 10 to the 9 newtons per square meter. So as you can see, the shear strain is unitless. So this will give you the same answer of 2 times 10 to the minus 4. And so that's it for this video. So now you know how to solve problems associated with Young's modulus, also known as the elastic modulus, and also the shear modulus. And you know how to calculate the stress and strain applied to different objects.